radiometers, and skip all this, I come back on this later, and consider only the lower right curves. For instance, this curve, if you are familiar with Bereitschaftsmagnetic field, you may perhaps be tempted to see in this curve already a slow brane field, although these curves are nothing else but noise, ambient noise. So we are forced to use a noise compensation technique, and the way how this is achieved is illustrated in the next transparency. So in each dewar we have 3 orthogonal pickup coils which are wound around a cube positioned 9 centimeters above an array of the biomagnetic pickup coils. Note that in the center this is also a cube which is completely wired for sensing the vector field, that is not only the radial component but also the 2 tangential components. By means of these 3 coils, once again displayed here, connected to squids, the weighted output of these squids is calculated and subtracted from the biomagnetic signal channels, one of which only is displayed here. So the output of this is the compensated signal, and the procedure might be put in the formula on the bottom, where we have the compensated signal as C by means of using these weighting factors Wx, Wy, and Wz. The question arises now how we can obtain the appropriate weighting factors, and from the literature we know that there are a number of techniques mainly dealing with the improvement of hardware gradiometers, because it's not easy to balance them completely, particularly in an environment of multi-channel system. The basic idea behind this method, which we call the covariance method, can be sketched by these 3 lines. Suppose we have a slowly varying noise which is seen by the compensation channel, in this we have only one, and also by the signal channel here, and on the signal channel there is some biological signal superimposed, and the idea of this method is to calculate the similarity between these 2 curves by means of calculating the covariance, deriving a scaling factor, so as by means of this scaling factor the difference of these curves will give us the compensated biological signal. So this is fine, but now imagine a quite different situation. At an extreme, assume that the ambient noise is very low, so this might be very flat, and the biological signal is very strong. In that case, the compensation channel would receive a small copy of the biological signal, and the covariance is dominated by the similarity of these 2 signals, and what comes out is a weight or weighting factor so as to that the signal cancels itself out, or with other words, you will have a gradiometer gain of 0. That's a situation you might object which will never occur, but what occurs in fact is that the ratio between the biological signal and the ambient noise varies, and as a consequence the scaling factor we obtain by this method varies, and the gain of your instrument varies, you don't have the same gain at the end of your experiment as you have at its beginning. So for this reason, we looked at an alternative method. It is fairly possible to simulate a hardware gradiometer by means of software. To this end, one has to expose the system successively in a homogeneous field of x direction, of y and of z direction, and trim these scaling factors so that the compensation signal is 0 in any case. Practically, this is done by calculating the signal amplitudes AXX, AXY, and AXZ in the case of an external X field, and the amplitude of the sensor signal AXS, and repeat that for the Y and for the Z field, and invert that matrix with the gain or weighting factors Wx and so on as the solution. So for a practical realization, we decided to apply the magnetic field from outside our chamber by means of large coils. The display shows the generation of the Y field that is across the door of the chamber. The current is a sinusoid, and the amplitudes are calculated by means of harmonic analysis. So now comes the next problem. If we try to find out to which degree the field which is used to calculate the weighting factors is suppressed itself, we should expect that the suppression should be down to the intrinsic noise level. This was not the case, however. These three lines show the vector amplitudes of the uncompensated signal, and after compensation we reach down here, and in the worst case the amount of compensation, that is at the external Y field through the door, amounted to only 42 dBs. Now this imperfection can be traced back to phase differences between our signal and compensation channels, probably induced by the way how we applied the external field and in collaboration with the chamber, which has a considerable inhomogeneity or anisotropy. Now we tried to overcome this problem. In the upper diagram we see again the uncompensated signal and the signal after compensation, which has a residual amplitude and is not 0 and has a typical phase shift of about 90 degrees. This is done with this procedure, and we generalize the procedure to account for the phase shifts by using complex weighting factors, and we could then suppress the field which is used to calculate the weights down to 0. It is, however, important to know how this method works for other noise sources, and in some cases, like a loudspeaker which is turned, this method works quite satisfactory. This is before compensation, this is after compensation, but the method still has one limitation and one disadvantage. The limitation is based on the fact that we only have gradiometers of first order, so we can only hope to suppress noise fields which have no gradients in the chamber, or if they all have gradients of constant amount or stationary gradients. So the software gradiometers of first order cannot eliminate the ambient noise of all noise sources at the optimum. The second, the disadvantage, is that for accounting, if we account for the phase shifts, we have to use back and forth transformations in the frequency range. This costs computer time, and the method is not very feasible, particularly if you would like to use it for online purposes, such as the display of your experiment on a graphic screen. Therefore, we used a low-cost version of this method by neglecting again the phases of the complex weights, and tried what we could do, and that this method is not working so bad at all can, I hope, be demonstrated by means of the data we acquired meanwhile. So I should explain this a little bit better. We simultaneously record the EEG and the MEG. The EEG channels are shown here with the physical notation, that is, positive is up. The MEG channels run from channel 25 to 13 according to this scheme, with the squares representing the MEGs and the dots representing the EEG. And those who are familiar with the Bereitschaftsmagnetic field would probably agree that, for instance, these curves here show some similarity, which are what we expect. And if I go back to the transparency I showed you first, this is actually the field preceding the flexion of the right finger, and I overlay the flexion of the left index finger. So you would certainly agree with me that the time course of the noise signals are very different, whereas at least in this region the brain magnetic fields are similar, and examples like this make us confident that we are dealing here with brain slow fields and not with noise slow fields. Thank you for listening.
Thank you, Dr. Jürgens. The paper is open for discussion. Are there any questions or comments?
One signal you're bound to be to have problems with is the signal from the heart. How do you deal with it?
Please speak again.
One of the problems you're bound to have is compensating for the signal from the heart. Yes, from the heart.
Yes.
How do you deal with this?
Our system is not very suited for recording from the heart because its surface is curved.
Compensation.
Oh, as noise. I did not speak about noise from the body. These are near noise sources and are very have a steeper gradient than the far noise sources, and as I mentioned, this is a disadvantage of the first order gradiometers, because they cannot completely throw out these signals stemming from the heart.
Are there other questions? I realized that your magnetic channels exhibited were quite noisy. Is it true? And this noise didn't seem to be spatial correlated, so I think it's squid noise or noise which is not an ambient noise.
The squid noise is not at the state of the art, of course, since we use radio frequency squids. It assumes about 30 to 40 femtotesla per square root of hertz at 1 hertz after compensation, or about 20 femtotesla before compensation. But the limiting factor here can also be seen if you consider the tangential components, which are not displayed here. The channels 25 and 26, no, 26 and 27 are X and Y channels. So we can compare the radial channel and the tangential channels, and we see that the biological noise is the limiting factor in this case.
Are there other questions or comments to this paper? You want to make another? If not, so we conclude this first part of the morning session. We will have the coffee break now because, yes, just a moment, because we have included some other speakers in the morning session.
Thank you. Now, we are going to go on the trip that we all decided yesterday, right? So, let me tell you a few things about that. First of all, we have a few extra speakers. We have Silvia Comani, who is going to talk on what I call extra nervous system paper. That is, we'll hear a few things about magnetocardiography. And we have Dr. De Leon, whom I'm going to ask, if possible, to speak this morning. Then we're going to take the trip. We're going to leave here at 12:30 sharp. We're going to come back and finish with the evening session then. And I want your promise that everybody will be for the evening session, because otherwise the rest of the speakers of the day, will be short-changed, and this is not right. Do I have that promise? Okay, then we have a very short...
To have the segmentation of isolated object of interest in the brain or in other part of the body, and after obtaining this image, very often these images are obtaining through anatomic image device like CAT or like NMR, but also through functional device. And I'm sorry I forgot my gamma centi and other images, but all procedures here are also applicable to functional imaging objects. Okay. If you want to match images coming from an atlas, a reference atlas, to objects corresponding to real object for an individual, taken through NMR or through CAT, you have firstly to segment real object. And one procedure of segmentation on a bone, very simple object, could correspond, for example, could correspond to the following procedure. You start with a sphere. On the sphere you have the meridian and parallel network. And progressively you are deforming this sphere in order to have exactly the contour of the object. And I am presenting the sequence of the deformation of this initial sphere, and I am keeping the network of the meridian and parallel and following the deformation of this geodesic network. And it's the first time of the procedure, iterative procedure. The second the object is taking a new degree of homotopy, that is, we are obliged to represent here this inner part of the vertebra, the medullary canal, and this following sequence. We are optimizing progressively a criterion in which we are minimizing the surface, external surface, the inner volume, and we are minimizing the inverse of the total variation of the gradient of the gray level on the surface. And progressively, we are going to an object having on the boundary a very big variation of the gray level. And the gray level coming from NMR or coming from a cat can, in the functional imaging, be the level of a magnetic potential, electric potential. It's exactly the same. And progressively, we have the appearance of the final vertebra here, and the final object is here. And we have kept, for simplicity, we have kept the initial network of geodesic of the object. Okay. And in fact, we are now belonging completely the object. We have in each point the 3-cubic polynomial fitting exactly the boundary of the object. That we are calling that a spline function, and we are able to have in a very minimum file the exact boundary of the object we want. I have a sequence of slides now showing practically the same, and our algorithms are in general based on a similarity, a metaphor between the action of neural networks. And neural networks, if you have represented, for example, the frequency of discharge, the firing of neurons by white cells at very low frequency of discharge by gray cells and no silent neurons by black cells, we have, in fact, if you are making a kind of a very comparison with a high level of considering this object, we have an image, in fact, here. And what is the next slide, please? Yeah, in another image network. What's the action of such network in general? This network was mimicking the cochlear nucleus just after the basilar membrane. And the work of this network is to treat the information coming from the gray level is in false color here. And when you have an orange or a red, you have a big gray level. When you have a blue or a green color, you have a very low gray level. But the interesting object is here is this object. This object has a certain homogeneity, and the distinction of this object between the other in its environment is the mean level is practically the mean level of the rest of the image. But there is a coherence, local coherence, and the neural networks, it's exactly the way in which the cochlear nucleus is extracting the vowels in a low frequency and high frequency noised environment, is extracting the fact that on the bound, at the interval of frequency, the vowels have practically the same, level on the Fourier power spectrum, for example. Bon. After applying my neural network, what appears? This region has been changed. It's a zoom on my square. This region a change of level. In fact, its level, which was the mean level of the whole image, has been increased because it is now practically orange or red. And next line, if I am representing sun in z-axis, the initial small square was c square, and after action of my neural networks, yeah, next slide. Okay. There is first slide, the next one, please. Yeah, I have extracted the inner coherence of the image in order to have a kind of gradient and boundary enhancement, preparing the segmentation. The next one. The next one is an example also of a bone, in which we are exploiting this enhancement on the boundary of the gradient on the boundary of the object. The next one, that prepares the automatic segmentation here by thresholding or by other methods. It's not my purpose to enter in the details of the final contouring. You have a contouring on each slice, 2D slice, and by collecting that, next slide, please. Oh, God. It's my slides this time. Yeah, they are thin. It's probably the reason. The 2D contouring is you can display the collection of 2D in order to have a skeletal representation of the object of interest. Next slide. Or you can smooth this skeletal representation in order to have a more realistic representation. And the problem is you have the faculty to play with each object because you are knowing exactly the place and locally the polynomial representing the boundary of each object. And an example of play is, oh my God. Now they are too thin. I think it would be preferable to change the slide directly on the. So this chronosupination movement, you can isolate the different bones of the wrist. The calf part of the wrist. More complicated objects. In the brain, objects are more complicated than those. But in general, the object of interest, physiological or pathological objects, have the following property. For example, a pathological object is a tumor, have a certain coherence, an inner coherence, because each cells are deriving from the same mother cells. They have the same response in cat or in NMR. And we will exploit exactly the same properties as the bone, this property of local coherence of the object, to segment the object. It's available for a pathologic object and also for a physiologic object. We will,